Section 3.4 is linear programming. I can solve problems using linear programming. Big ideas here. Some real-world problems involve multiple linear relationships. Linear programming accounts for all of these linear relationships and gives a solution to the problem. The feasible region contains all the points that satisfy all the constraints, and those are restrictions on the variable. Again, linear programming is a method for finding the minimum or maximum value of some quantity, given a set of constraints. The restraints form a system of inequalities. The solution set of the system of inequalities is called the feasible region. So we're going to graph all of our inequalities, and the part that's our solution, that's going to be our feasible region, the part that works. The quantity we're trying to maximize or minimize is modeled with an objective function. Oftentimes it's cost or profit. So if it's cost, we're trying to minimize it. If it's profit, we're trying to maximize it. If there's a minimum or a maximum value of the linear objective, it occurs at one or more vertices of the feasible region. And our vertices are just the corners or the points where our shape changes. We can solve a problem using linear programming by testing all of our vertices in the objective function. So in example 1 here, what point in the feasible region maximizes p for the objective function p equals 2x plus y? So profit equals 2x plus y, and we want to maximize p. So in order to do that, the first thing we're going to do is we are going to graph our system of inequalities and find the part that is our solution set. So it looks like we have a lot going on here, guys. But x greater than or equal to 0 and y greater than or equal to 0 just tells us that we are in the first quadrant. It means our x's have to be positive and our y's have to be positive or 0. So we're just going to deal with the first quadrant. So I'm going to graph just these two, and again, only in the first quadrant. So I'm going to solve the first one for y. Subtract an x to both sides. Divide everything by 2. I'm going to put this in slope-intercept form by putting my x first. Remember, our coefficient on that x is a 1, so it's minus 1/2 x plus 5/2 or 2.5. So I'm going to start at 2.5 as my intercept. I'm going to go down 1 over 2, down 1 over 2 for my slope. And I'm going to connect that because it's equal to. So I'm going to use a straight edge here to connect. And it looks like that. For my yellow line here, we want it to be less than. So we want everything in this part. Now, my second line here, I'm going to solve for y. Subtract an x. We could also use intercepts. Divide everything by -1. But when we divide by -1, remember we have to flip our inequality. So I get positive x minus 2. So I'm going to start at -2, go up 1 over 1. Keep in mind I'm only going to graph this in the first quadrant because I need x and y to be greater than 0. So my graph here for my red line, even though my intercept is at -2, I'm not going to start until I get into the first quadrant. And it's going to look like that. And here, because we continue off into the first quadrant, I can put an arrow. We want our y values, everything to be greater than x here. So my shading is going to be above my line, everything here. So the part where they overlap is my solution. So just in here is my feasible region. Okay, just this part right here is my feasible region. Everything else I can erase. So now that we have our feasible region, we're going to pick our vertices out. Those are the points that are going to have to be tested in our objective function. Here I have 4 of them. And again, those are the corners or the places where our shape changes direction. So my points here are 0, 2.5, 0, 0, 2, 0, and 3, 1. Those are all of my vertices, okay? and my maximum or minimum has to happen at one of those points. So I take those points and plug them in to my objective function here for profit. So 2 times x plus y, 2 times x plus y, 2 times x plus y, and 2 times x plus y. And we want to know what point maximizes p, which means gives us the biggest value. And that happens here. So my point is 3, 1. So x is 3, y is 1 is going to be the point that maximizes profit for this function. So again, we graphed our inequalities, found our feasible region, picked our vertices, plugged them in, and found the one that did what we needed it to do. We needed it to maximize, so we picked the biggest one, which was 7, is the value of that, and the ordered pair, or the point where that happens, is 3, 1. Now, using the same constraints from example 1, so the same graph, same feasible region, and same vertices, but here our objective function changed. We want to know what values of x and y maximize p here. So again, my points were 0, 0, 0, 2.5, 2, 0, and 3, 1. I plug those into my function here, profit function. X plus 3 times y. X plus 3 times y. And x plus 3 times y. Here, our maximum value is 7.5, and that occurs at 0, 2.5. So my point actually changed. It has a maximum of 7.5 at the point 0, 2.5. So the values of x and y that maximize p are right here. In example 2, we're screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival and are working with the following constraints. These are on page 159. We have at most 20 hours to make shirts. We want to spend no more than $600 on supplies, and we want to have at least 50 items to sell. It also tells us some more information here. It tells us for t-shirts, it takes 10 minutes. Supplies are $4. And the profit is $6. And then for sweatshirts, it takes 30 minutes. It is $20 for supplies. And $20 profit. So our constraints here. First of all, we're talking t-shirts and sweatshirts. So the amount of t-shirts we make can't be negative. Has to be greater than or equal to 0. And the amount of sweatshirts that we make has to be greater than or equal to 0. Can't have negative amounts of those. Okay, now we have at most 20 hours to make t-shirts. It takes 10 minutes, to make shirts. 10 minutes per t-shirt. So 10 times the number of t-shirts. 10 minutes times the number of t-shirts gives us our time spent on t-shirts. And 30 minutes for sweatshirts. So 30 minutes times the number of sweatshirts. We have at most 20 hours. So we can spend 18 hours if we wanted, but we can't spend 30. We can spend less time or equal to, but we can't spend more. Keep in mind our labels have to be the same. So if I'm talking minutes here and minutes here, I have to switch my hours to minutes, which I do by multiplying by 60, and I get 1,200 minutes. So 10 minutes per t-shirt and 30 minutes per sweatshirt. That has to be less than or equal to 120 minutes. Okay, we want to spend no more than $600 on supplies. Well, supplies for t-shirts are $4. and supplies for sweatshirts are $20. We want to spend no more than $600. So here we could spend exactly $600. We could spend $500. We can't spend $700. So we could spend less than or equal to $600. And the last thing here is we want to have at least 50 items to sell. So the total items is our t-shirts and sweatshirts. In order to have at least 50, we could have 50. We could also have 60, but we can't just have 40 in order to have at least 60. So greater than or equal to 50 there. Now, if we look, we've got some big intercepts here. My t-shirt intercept in this one would be 120. Here would be 150. I don't really want to graph that by hand. It's not going to be very accurate. So instead, what we're going to do is we are going to go to Desmos. Keep in mind that we're trying to maximize profit here. And our profit function, it says our profit for t-shirts is $6. So 6 times the number of t-shirts. And our profit for sweatshirts is $20. So 20 times the number of sweatshirts. Okay, I'm going to make t-shirts X while we graph, and sweatshirts Y, just for simplicity when I go to Desmos here. And again, it's desmos.com/calculator, or you can use the app. My first function, 10x plus 30y is less than or equal to 1200. I have x plus y is greater than or equal to 50. I have my cost, which is 4x for supplies, plus 20y, less than or equal to 600. And then I have the fact that t-shirts have to be greater than or equal to 0, and sweatshirts have to be greater than or equal to 0. Now, this looks like a mess. I can't really see what's going on, so I'm going to zoom out a little bit. There we go. I can see all my functions a little bit better. And what I can do is I can just kind of scroll here so that I am just looking at my first quadrant. And that allows me to click off these two, which makes it a little bit easier to tell what I'm looking at here. So the points for my vertices are those 4. My feasible region is in between those 4 points. That's where all 3 overlap. And if you're not sure, we can turn these on and off by color, but that's our darkest spot where all 3 colors are. Okay, so I have our points here. I'm going to plug them into our profit function, which again is our profit for t-shirts, $6, and our profits for sweatshirt, $20. And I'm just plugging in my x's and my y's to each point. So my x is in for my x, and my y's in for my y's. And we wanted to maximize profit. So if we look here, our profit is biggest right here, which means 75 and 15. So how many t-shirts? 75 t-shirts. And how many sweatshirts? 15 sweatshirts. And that's going to be what maximizes our profit, because our profit 750 is bigger than 720, 650, or 300. Some real-world problems involve multiple linear relationships. Linear programming accounts for all of these linear relationships and gives a solution to the problem. The feasible region contains all the points that satisfy all of the constraints or restrictions on the variables. And that's all I have for section 3.4.